Okay, hello. I'm Beatriz Raposo de Medeiros, and I am a phonetician at Department of Linguistics at the University of São Paulo, Universidade de São Paulo. And I'm also coordinating the Phonetics Committee of Abralin. Today, I will be the discussant of this Abralin online that brings the linguist Khalil Iskarous. So, Abralin ao Vivo, Linguists Online, is designed to give students and researchers free access to state-of-the-art discussions on the most diverse topics related to the study of human language. I have the great joy to present you Khalil Iskarous that will talk about sound structure and deep learning, a hope for endangered language documentation. Okay, Khalil is associate professor at the University of Southern California. He is interested in phonetics, phonology, and computational linguistics. He uses the principles of dynamical systems analysis to try to understand the relation between language and other motor systems in biology like worms and octopus. He obtained his PhD in the University of Illinois under the direction of Jennifer Cole, and spent 10 years as a research scientist at Haskins Laboratories. His work supported by the National Science Foundation. Okay, so Khalil, be very welcome. It's a joy to have you with us. And the mic and cam are all yours.
Great. Thank you so much. Thank you so much, Bia and Miguel and the Phonetics Committee. I'm really happy to be presenting to my Brazilian friends. I haven't been to Brazil for a few years, but it's always nice to be there, and it's always nice to be with you, even if it's remotely. So let me share my screen. Okay. So, okay. So let me give you an outline first of my talk, and then we'll start. So I'll briefly outline the problem of endangered language documentation and revitalization and various solutions that are occurring. Then I'm going to tell you about why deep learning could be of any use, and also what is the most it can offer. And then I'm going to give you a conceptual introduction to deep learning in its static and dynamic instantiations, and tell you why it could be related to language, especially endangered language documentation. And I'll give some illustrations. And I'll also talk towards the end a little bit about acoustic modeling, and I'll provide some illustrations as we go of the use of deep learning on the problems of acoustic labeling, and a little bit about phonotactics. And then I'll conclude with some general comments regarding endangered language documentation and its place in the study of language. Okay. So everything is fine? You can hear me and everything? Okay. So, you know, as we start, I just want to kind of remotivate why we study endangered languages. So the loss of languages, not only loss for the communities that lose their cultures and to world culture as a whole, I believe it's also a loss for the human ability to understand motor control, perception, cognition, social, and other kinds of organization. And that's why I think the study of endangered languages is really fundamental. It's about all of us. It's not just about the communities that are losing their languages. And sometimes I hear this sort of a concept that I believe is false, and I want to just lay it out as being false, which is that language endangerment and loss is some kind of natural process, is part of some kind of natural process. You know, languages are born, languages die, and this is just sort of part of how nature works. I think language death is not part of any kind of natural process of language birth and death. As we know, most languages are lost at gunpoint. Sometimes literally, very often it's literally at gunpoint, but most often, quite often, it's also through economic, social, psychological marginalization. But I don't believe that it's part of any kind of language death, some kind of natural process of language death. And I think it's important to point this out because many people wonder, like, why should we be paying so much attention to endangered languages if it's part of some kind of natural process of attrition and death? There's nothing natural about it. And the activist part of me has always wanted to get involved with this problem because it's nothing but natural. So the main methods of endangered language documentation will always be through careful human engagement and analysis with communities that are losing their languages. So by talking in this discussion about deep learning and technology and how it can help endangered language documentation, I don't mean to suggest that in any way these automatic methods are going to replace usual kind of linguistic analysis that involves very close analysis by humans through interaction with speakers of the languages exhibiting linguistic attrition and death. The question is, can automatic methods help? It's not, can automatic methods replace the usual way we do endangered language documentation? That is not the question. The question is, can these methods help? And that's what my concern is here, because I do think they can, and they can be of great use as they evolve. So several attempts are being made to use deep learning to assist in the solution. And my goal here is to give a feel for why these methods ought to work and feel for what they actually do. Technology obviously can help in many ways with endangered languages. For instance, many people have used the technology of deep learning as it exists and train it on lots of existing languages with lots and lots of spoken data, and then using it on endangered languages or languages that the system has never seen, and they work extremely well. And I do not mean in my talk to be in any way marginalizing these methods, but I think that there can be other methods that are using far less data, which is what I'm going to talk about. But I think, again, it's not a zero-sum game. These kinds of methods will continue. Then there are other kinds of technologies like remote recording. So many people have generated apps on mobile phones that are set up to collect, to allow people to record data that is then transferred over the network when it's hard to access actual speakers so they're contacted through some kind of community leader. And these kinds of things are incredibly useful and incredibly good. But what I'm going to talk about is of a different nature. So for instance, in the work that I've been doing with Alessandro Vietti on the Ladin language in the Fassa Valley in northern Italy, we've been creating, for instance, things like picture books where my students have, specifically Jackie Andrews, has generated this beautiful art for very small children as a mobile app. And then they hear the voice of a native speaker,
Nina Nana per Ladin,
which is about a child going to sleep. And they're watching these pictures as they go. And it's a way for them to be entertained by their, to be entertained by the language that they are, that's their native language. so that if their caretakers are speaking to them in their, in their endangered native language, they
Khalil,
have yes.
Sorry to interrupt you. For me, it's fine. I have a good screen here, but someone told maybe you have to put in the presentation mode. I thought it was in the presentation
mode. Okay. It's
mode.
not in presentation mode, but I'm afraid that it's going to cut off some of the. Well, I'll put it in presentation mode, but I think it's going to cut off a little bit.
But do we? Yeah, okay, maybe it's easier for them to.
Okay, that's fine. Thank you. Thank you. And what I'm really interested in is in using, for instance, deep learning, not just for documentation, but for generating very simple video games that have audio in them. So where a child says something to play some sort of game. And that would really help with where we would be using deep learning to do a very small amount of speech recognition that's actually helping a child learn a language. Again, if the caretakers aren't speaking to the child in the language, they're not going to learn it. But what very often happens, for instance, in the particular situation where we've collected this data, the dominant language, Italian, is what very often the children will primarily learn, because that's the language of their friends, and it's the language of all the books that are read to them, and the entertainment that they're provided with, etc. Whereas we're trying to provide additional modes of learning the language, and AI could really be helpful in this kind of thing. Okay, so sound or visual action for sign language is the first linguistic signal. So we ask the question, to what extent can this be successfully automatically transcribed? Because if it can, then both documentation and revitalization projects that Alessandro and I are involved in could be assisted a great deal. So for languages that are like English and Mandarin, etc., there is unlimited data, and machine learning has been most often used for these. Whereas our situation is what people have called a zero resource problem. There is really hardly any data. So to what extent can deep learning techniques be extended to the zero resource problem that people like Sharon Goldwater and her colleagues have worked on quite intensively? So, and since speech or visual information are the first kind of signal, we need to start there. Now, I would like to mention here that in the last 2-3 years, a very interesting thing has occurred within the artificial intelligence community itself, which is there has been a great deal of recognition that current methods of artificial intelligence are incredibly inefficient and require way, way too much data. And as a matter of fact, the 3 winners of the Turing Prize, the highest prize in computer science in 2018, which won the Turing Prize for their work on deep learning, have all talked about the need for what Jan LeCun has called self-supervised learning, which requires far, far less data than. So what I mean to suggest here is that even within areas where there is an enormous amount of data, lots of work in AI is tending towards the use of far less data. So this is very helpful for us in our interest in endangered languages, because that's where the tendency is going anyway. And now I would like to address something that linguists are very interested in, which is why can it be useful? I don't want to just sort of show you methods and illustrations. Oh, it works. I'd like to talk about why can deep learning be useful? So every language has a large number of laws structuring the production of language. There is neural computation at many levels: motor control, acoustics, aeroacoustics, syllabification, prosody, morphosyntactic combination, semantic interpretation, all kinds of pragmatic principles, discourse structure, etc. These laws, these structures impose a great deal of redundancy and predictability in the signal that the structuralists and the generativists have focused on for the last 120 years, and even before that, obviously. So what makes deep learning interesting is that all it is a set of advanced signal processing and statistical methods for reducing redundancy in data, making use of the notion of distribution. So that same idea of distribution, paradigmatic and syntagmatic, that the likes of Trubetskoy, Zelig-Harris, Chomsky have focused on, and a lot of what linguistic analysis at all of its levels focuses on, how redundancy and predictability arises in language, being introduced by the laws at these various levels. Whereas deep learning is an inverse method. It is a method for detecting redundancy, eliminating redundancy so that what remains is that which is novel, the novel information. So deep learning isn't just a cool thing. It ought to work. And I would claim that it will work for our purposes if current efforts within deep learning technology for extracting order and eliminating redundancy using far less data are successful. So that's an important caveat. And what I just told you is a bit different from what you would hear from people in artificial intelligence. And sorry to be sort of uncharitable here, but most of the time you'll just hear, deep learning is just brand new, fancy magic, and it has to work since it always works, and it's fancy and it's new and it's amazing, and look at it and let's just use it. It's really it is a set of advanced statistics and signal processing using very creative extensions of those ideas that we already know about in our study of phonetics and our study of statistics. But it's really, really an inverse tool that is based on things that we know a lot about: predictability and redundancy. And I think this is really important for linguists to know as they apply these kinds of tools. It's really not magic at all. Historically, it's an extension of well understood and well-known methods, but it's really treating the redundancy that we already know about. Now, the bad news is we're very far from solving the full problem. So this is from the abstract of a paper that just came out a couple of months ago from a group at Facebook on a speech recognition system called Wave2Vec, which is a self-supervised system. Down here, it tells you it's very nice because it's using 10 minutes of labeled data, which is excellent because previous systems would require many thousands of hours of labeled data. But it needs pre-training on 53,000 hours of unlabeled data. Well, no endangered language is going to, or very few endangered languages are going to be able to provide us with 53,000 hours of even unlabeled data. So we're actually getting there because just a couple of years ago, no one would have said we're only using 10 minutes of labeled data. So this is an enormous, enormous set of advances, but we're certainly not there yet. And I hope you're not expecting me to give you this talk, expecting that I will tell you, here's a program, collect your data from your endangered language, put it in the program, it's going to transcribe it, extract the structure, and you don't have to do anything. That's not what I'm going to provide, because if that's what I figured out how to do, I wouldn't be sitting here talking to you. I would just be like, sitting somewhere with lots of cash, because I would have solved the speech recognition problem, and I certainly haven't. So it's important to understand the limitations of these kinds of, the current limitations of these kinds of techniques, while still understanding why we ought to have hope that they will work. And as we go, I'll provide you with a little bit of more of a conceptual understanding of, and we'll limit ourselves. So what this paper is about is actual word identification, whereas what we're going to be interested in is acoustic labeling. If you've collected data from an endangered language of several minutes, can you use tools from deep learning to help you label frames and segments in this data? I think that's extremely useful for anyone collecting data in the field. And that's something that I'm very, very interested in. So I'm now going to provide you with a conceptual understanding of deep learning before I show you the particular illustrations that I've done with various colleagues. So the first thing we do when we're starting to do deep learning is to numericize the data. And for speech and visual signals, this is easy because it's already numerical. So speech, we have a spectrum, or we have a waveform, and it has numbers. Or if one is working on sign languages, then one has pixels that are changing in a visual field. We will call these, however, cognitive symbols, like phonemes, morphemes, words, etc., can also be numerically symbolized. And people have known this for many decades. People like Paul Smolenski and many other people have worked with these kinds of numerical representation. So imagine you have a language in which you believe there are, let's say, 41 phonemes, as we'll see later on in a particular illustration. And you're trying to detect phonotactic structure from words of the language. Then each phoneme would get a list of numbers we call a vector of all zeros and a single one. And we distinguish the 41 by each of them having a 1 in a different location. So this is each symbol, each phoneme in this case, has a symbolic list of numbers associated with it that distinguishes it from all the other elements of the set. It's a very, very stupid seeming kind of characterization that is numerical, but I will show you how from it we derive much more interesting numericizations. And this is what people in AI call one-hot encoding. So we will call this vector or set of vectors A1, the activations at time 1. Then we process this vector or these vectors from the initial representation with things like plus, times, and a nonlinear function, for instance, the logistic function that you already know from statistics. So I emphasize here that the functions being used are incredibly simple. And that's part of the power of AI, is the ability to combine very, very simple computations requiring nothing but arithmetic operations like plus and times, and combining them molecularly with each other to obtain very powerful computation. So we take those initial numerical representation A1 and we process them with some known numbers that we have already learned. I will tell you how we learned them in a few minutes, but we'll assume that we've already learned these numbers. Let's say we'll call them W2. And we will use the W2s to multiply, add, and use the logistic on A1 to obtain a second representation, A2, that has generalized over the input A1. So A2 is a set of numbers that has abstracted over some of the correlations in A1. Then we process the numbers in A2 numerically with some already learned parameters, let's call them A3, to get some yet another intermediate vectors of numbers A3 that have generalized over A2. And we keep doing the same thing over and over again, and that's what deep in deep learning means. Till we get some maximally compressed representation, or we sometimes call it active set of activations, like neural activations, that are a maximally abstract, compressed representation of the input, stripped from its redundancy. So deep learning works by successively compressed representation, or I would like to call them even thought vectors, because they're not input-output systems as most people think of them, because they're developing intermediate representations. And deep in deep learning means how many intermediate representations of your input data are you acquiring. And you can think of it as principal components analysis if you're familiar with that, but it's a nonlinear form of principal components analysis. And it's principal components over principal components over principal components. So it's deep nonlinear principal components. That's one way of thinking about it. So what I'm telling you is that there is no magic here. It is a method that is really nicely fitted to signals that have an enormous amount of structure in it through laws that have added structure. And they are systems that are able to decompress the data, get rid of the redundancy, and really see the simplest form of the representation. Now, where do these W's come from? Because right now they seem like magic. How do we know these W's? Well, they actually start out random, and then we learn better versions of these W's by solving some kind of task. And this is now crucial, where distribution in the data is made use of. So the distribution, the structure, the redundancy in the data is used in order to make us learn better W's. And that's how deep learning works. It has knowledge through, so knowledge that is numerically represented in these W's. It can apply the knowledge to realize more and more compressed representations. And it can learn this knowledge from tasks that require understanding of the patterns in the data. So if the W's catch on to the pattern in the data, they improve because they allow the system to strip the data of more redundancy. So I'm not providing you, because this is an hour lecture, I'm not providing you with the exact arithmetic, and it's really more or less arithmetic that's involved in how all of this is happening, but it really relies on 300 years of work, starting with Leibniz and going forward, that has culminated in this generation in incredibly powerful systems of of compression of information. And they work particularly well for things like vision, for language, and other kinds of systems in which an enormous amount of structure. In vision, a lot of it is our physical principles that structure light. There are the laws of reflection and color and texture, etc. For us, there are laws of linguistic structuring. So by the way, sometimes people are turned off by deep learning because they feel that if it's working for so many different applications, it means that it has nothing to do with language specifically. But the specific thing that makes it applicable to so many things is that so many things are built on laws. The laws can be of very different nature, but if they introduce redundancy, then deep learning works on them. Okay. It's funny to be talking in this medium because usually I would pause and ask people for if they have any questions, but I have to keep going. Okay. So I'm now going to show you a very particular neural network called an autoencoder. And this may look like a very complex kind of graph, but I'm going to take you through it. So what we're seeing here is as if we are dealing with, for instance, so take the A1s to be spectra. Each spectrum lasts for 20 milliseconds from, let's say, a 20-minute conversation. So we take a 20-minute conversation, cut it up into 20 millisecond intervals, and let's say for each interval, we could use the waveform, but let's say we use a spectrum of the waveform. And that's our numerical representation of some acoustic event happening over just 20 milliseconds. Now we take every such spectrum, and these points here, I think there are 20 points here. So we're just going to, I'm sorry to have made this 20 and 20. So it has nothing to do with the fact that there are 20. It could have been a different number, obviously. But imagine that our vector has 20 entries in it. Okay. We will have learned a set of numbers W2 that when you use multiplication, addition, and logistic functions, we can take this A1 and compress it into A2. And we take the A2 and compress it with numbers W3 into the most compressed version. So we've gone from 20 numbers that are highly correlated to 2 numbers that are maximally decorrelated. And then we re-expand the representation to, let's say, A4, and then to the last A. Such that, here is now the task, such that A1 equals A end. Okay? So I take a spectrum. Imagine the spectrum is of the vowel A. So I put it here. I compress it and then decompress it. And I hope that my W2, W3, W4, and W5 acted in such a way with multiplications, logistics, and additions to reproduce the exact set of numbers here at the end. And then I give it another spectrum, maybe during a pause. And it's supposed to reproduce that spectrum of the pause. And then maybe I give it a little portion of an S, and it's supposed to reproduce the S. So, but the amazing thing is this, the W2s, W3s, W4, and W5s have to be such that whatever sound I give it, it compresses down to 2 numbers, and then uncompress to provide the same set of numbers. Now, if your data has paradigmatic order, meaning if you have, let's say, 30 or 40 kinds of segments in your linguistic system, representing roughly 30 or 40 spectral shapes that contrast with each other paradigmatically, this tool will provide a 2-number code representing all the information that you gave it as 20 numbers. And what we end up doing after that is using the network like this. After we have trained the W2s, W3s, W4s, and W5s to accomplish this task by giving it lots of spectra, asking it to reconstruct those spectra from a very small number of elements. When we've successfully done that, we now throw away this part and this whole part of the network, and the network is stripped down to this. And now we give it each spectrum again. Now we multiply by the W's here and here, and we add and all of this stuff. And now for every 20 numbers, we get 2 numbers. So we have compressed the information in the 20 numbers into 2 numbers. Obviously, these don't have to have been 20. They could have been 128, as I will show you in a few minutes. So our compression could be from 128 numbers to 2 numbers. But those 2 numbers have to be so good as to be able to reconstruct the entire spectrum. And the numbers that we've learned, these W's, have to be so good that it has to reconstruct an A from an A, an U from an U, an E from an E, an S from an S, an Esh from an Esh, etc. So the difference in the spectra over the data set has this paradigmatic contrast. So not every spectrum is different from every other spectrum. There is redundancy. And this autoencoder will provide you with a very good 2-number code for, let's say, 128 numbers. And you know what? This is what we as linguists do. This is an automatic device that is doing something. So people who don't do acoustic phonetics may not think very much about this, but well, when you're, when you're looking at a spectrogram, you see spectra, 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 and then let's say spectra over 150 milliseconds are from a single segment, or maybe 2 overlapping segments, or these things can be accounted for as well. And the paradigmatic contrast within the system of spectra is caught on by this device. So now I'm going to give you an example from a non-endangered language of English, but it's just a very sort of, it's a kind of task that's very, very simple that tells us whether such a system could even work at all. So what I'm showing you here are data from 1,668 vowels that James Hillenbrand put together in 1995. This is a database of English vowels produced by males, females, and children. Sorry for the gendered language. Producing 12 American English vowels. And each spectrum has 128 numbers. And what I'm showing you here in red are the spectra of different vowels. So this is the vowel E in red. This is the vowel A. This is another. So these are just randomly chosen spectra. And they are, what you see in blue are the reconstructions of the spectra from a 6-number code. So we call these circles that I showed you neurons. That's why we call them neural networks. And what you see in blue is a reconstruction of the spectrum that you can see is pretty good from 6 numbers. So we've done a compression from 128 numbers to 6 numbers. By the way, why are we so concerned? I may have not made this point so clear. Why are we so concerned about compression? Well, if we have a file that we've collected from an endangered language, we would like to label every frame of that file phonetically. And if we don't want to label it with 128 numbers, because that's too many. We want to label it with maybe 20 or 30 labels. And those labels could come from a code that's, let's say, 6 numbers long, or even better, 2 numbers long. So this is the same data, but you see here the reconstructions from 2 numbers only. And this is pretty good. As a person who does acoustic phonetics, it's not perfect, certainly, but to be able to reproduce 128 numbers from 2 numbers is pretty good, because you see here it's getting the fact that in a back vowel, where you have 2 formants that have come very, very close to each other, it's still resolving both formants, you see. And again, here you see F2 and F3 becoming very close together. And it's getting the fact that if it's a bad reconstruction, it would be drawing one big dome here that's missing out the fact that there are 2 close formants. Now, it may seem this is not a big deal. We've known since 1947, 48, through the work of Martinios, that we can extract the formants. And these are 2 numbers, and they represent. But if you've ever used Pratt, you know that detecting formants is not a very easy thing. These numbers that are extracted are not formants. They're a deeper entire spectrum descriptors that are describing the entire spectrum as a whole. And I would claim that they're better than formants, as they describe aspects of the entire spectrum. And there have been many papers that show that in perception, for instance, spectral shape matters, not just where the formants are. So bad news is that these numbers that we get are not in themselves interpretable like formants. However, people doing this kind of thing for vision have developed convolutional neural networks and convolutional autoencoders, which I will not discuss here, but where the numbers, the W's that you extract, and the activations that you develop, or these compressed numbers that you get from which you reconstruct, actually start to acquire a meaning. This is, by the way, a good example of an E where in reality F2 and F3 are very close together, but the reconstruction did not catch on to that. So it's put one big formant for F2 and F3. So this is a 2-neuron construction where this particular instance, it's not picking up on the fact that there are 2, it's not resolving F2 and F3, whereas it's resolving F1 and F2, which is nice here. But here's another instance of lack of resolution. So then we would have to use potentially a 3-neuron or a 4-neuron code. What I'm hoping to have illustrated to you is that these devices use numerical operations to do something that we already know principal components analysis and other kinds of techniques do, but far, far, far better. And I just wanted to give you a feel for those 2 numbers. So by plotting in red the E vowels from all 1,668 spectra. So the E is in red, the magenta is for E, the blue is for U, and the cyan is for U. So there are 4 high vowels of American English, and this is pretty good separation. The U is spread out. I think there is some fronting for some of the speakers, etc. But there is extremely, extremely good separation from a 2/128 compression, which is really quite excellent. If I were to show you a formant plot for these, it would not look as good as this. Okay, so let's now go on to some endangered language work. So, and this is collaborative work with Alessandro Vietti from the Free University of Bolzano. We have done work with students from USC over 2 years, and we're doing more work this summer on Ladin spoken in the Fassa Valley in the Alps in northern Italy. So what I'm illustrating for you here is, so our students interview native speakers of the language, and they record them, and then they document using Pratt. So they transcribe the data, etc. And what I'm showing you here is I took a single file that has 4.7 minutes of speech, which is a very, very small amount of speech data. And I'm not using any of the labels that the students provided. And I included all the frames. There were, I think, something like, 11,000 frames or so in this particular case. And I asked the question, if we run an autoencoder on all the spectra using a 2-neuron reconstruction, can enough be learned from an autoencoder? And I tried this structure. One could try many, many different structures. So we take the 128 spectrum, compressed into 100, the 100 into an 80, the 80 into a different representation of 80, different representation of 80, and then finally down to 2, and then reconstructing again from these. So you can think of it in terms of a latent variable vocabulary. We start out with our observed variables, which are 128. Then we go to 100 latent, then 80 latent, 80 latent, 80 latent, 2, and then back to 128. And these are the reconstructions. And you can tell they're not as good as when we just had 12 vowels from a very, very carefully. So this is the entire set. So it has fricatives and it has silence. It has all kinds of things that are happening. And it's not that great, but it's also not terrible. We get a bit better by going up to a 6-neuron bottleneck in our, and there you're starting to see good resolution for most of the data. Now, what do we do with this? Why is this of any interest? So sorry to have already talked for, oh, wow, without telling you what the application of this is, but here's an application. So here's a small portion from this where the speaker is pausing and saying, so it's a very long, and a good test is to see whether the same label is being provided over and over again. If this system worked perfectly, every single one of these frames would get exactly the same label. That is not happening. But most of them are either 12 or 13. So it's getting the fact that all of these are coming from the same cluster. So I ran k-means cluster on the codes. So to group similar ones into the same bag, I think I used 35 clusters. And you see that most of the time it's using the same number. And this is with a 2-neuron code. 20 out of the 35 frames, we get the same number, 13. A few of them are 12. Did I think I may have used the same one. Yeah, no. So this is the wrong picture, sorry. So this is supposed to be a different picture. But in my file, I put the same picture. And each time you run this, you're going to get a different code, obviously. But here, what we're looking for is consistency. So you see, this is not an unhelpful thing in labeling, because it's telling you that for quite a few frames, when the spectrum is not really changing, it's actually not changing in terms of this compressed label. Oh, this is the second one, sorry. This is the 2-neuron. Yeah. So now it's using mostly the code 11. So 20 out of the 35, it's using the code 11 for this. So, and obviously we could do a lot of optimization over this because k-means is a very poor cluster analysis, clustering mechanism. And I could optimize the number of clusters and we would even get better results. But this is already pretty good. And I'm hoping that you're starting to see a glimmer of why this could potentially be useful, because we want to label our data to start out with a something that we don't have to listen to bit by bit by bit by bit. It would be nice to have some assistance by a deep learning device. And this is what I mean by hope. It's not perfect, but it's some hope. And this is data that was collected by my colleagues, Maria Luisa Zubizarreta and Rumi Pancheva, and Abigail Jarvis, a student at USC, of Guarani spoken in Paraguay. And it's from a 2.5-minute file by a female. And these are the reconstructions from a 6-neuron code. And it's not bad at all. Here you see like clearly something that's a vowel where the formants are very close and it's resolving them. You don't always get resolution, but it's at least at the low frequencies, it's doing pretty well. And this is a similar kind of thing, except it's from 2 vowels. And what I just wanted to show you here, that when the vowel settles down, it's using the same label several times here, 15, here 9, here during the, I think it's a nasal, it's using 8. So there is quite a bit of consistency. However, there is so far in this autoencoder no concept of time or memory. Everything has been paradigmatic. There is no, I think it's raining in Southern California. It's great. There's nothing syntagmatic here, and there is no memory. If you have some notion of time, some of the kinds of things that we see here, which is like getting a 20 between a whole bunch of 11s, would be eliminated. So we want devices that have memory. So I'm going to now show you the first kind of device that has memory, which is still an autoencoder, but it's a syntagmatic autoencoder. So now I'd like you to shift attention from the acoustic labeling point of view to a lexicon. So here's a lexicon of English. So you have the word refer. It has r, followed by a, followed by f, followed by And here you have, different words and they're syllabified. And imagine we already have a syllabification like this, which is not available in most endangered languages, but the idea would be as the better we get for acoustic labeling, the more we can have things like this. But imagine that we already have a syllabified lexicon with phoneme labels. Then here's a syntagmatic fact coming from the phonotactics of a language like English. Vowels hate vowels after them, and they love consonants. Consonants hate consonants after them, but they love vowels. That's a fundamental fact about the wavy nature of syllables. Now imagine that we one-hot encode each segment in our set. And let's say we have 41. And now our autoencoder doesn't predict the same representation as the output. It predicts from the R one-hot encoding, it predicts the A one-hot encoding. From the F one-hot encoding, it predicts the one-hot encoding, etc. And I ran it for 10% of an English lexicon, and these are the results. For a 2-neuron code, the reds are the vowels and the blues are the consonants. You see, they're almost entirely non-overlapping, which is really quite beautiful. Now, there's nothing particularly new about this because Markov did this over Pushkin's poetry and deduced the notion of consonant and vowels from the poetry of Pushkin. And this was his first one of the first machine learning devices ever which was applied over very similar kind of data, except for Russian, obviously. And he developed his first finite state device, a Markov chain. And you can see this device is catching on a finite state aspect of language, because it's getting at, if I have this, the next thing should be that. And now I'm going to show you an even more impressive kind of device called a recurrent neural network. A recurrent neural network doesn't take a single vector, it takes a whole bunch of vectors. So I could give it the one-hot encodings for all the vectors in a word. Or if I'm doing sentential processing, I could give it vectors, each vector representing a word in a sentence. And this amazing device, an auto-encoding recurrent neural network, will take all of these and develop a single representation. So that's this green arrow. It'll develop one vector that has memorized the entire sentence or the entire word. And from it, it can reconstruct that entire set of vectors. So you give it lots and lots of words or lots and lots of sentences, and it's able to kind of stupidly reproduce these things. And with refinements called long short-term memory, it can have arbitrary memory that will forget some elements in the recent past. I can't remember what I had for breakfast, but I remember what my mom told me 3 or 4 days ago. And then I forgot what I had for dinner before that, but I remember, the last time I was on campus. So memory actually fluctuates. So within the recurrent neural network family, there are very, very sophisticated devices that allow us to have displacement. Something here in time affecting something here in time. And this was developed in 1986 by Jordan. Interestingly, these are pictures from his paper from 1986, which was a UC San Diego dissertation, and his application was to nothing other than coarticulation. So this is a picture of a reconstruction of coarticulated speech. And here's another picture of a limit cycle, what people use in articulatory phonology to represent speech. So there is a lot of rich history, actually, of interaction between deep learning and phonetics that sadly very few people know about. If you'd like to read more about this, I have a paper from 2017 in Journal of Phonetics that talks about this. Now, it may seem that RNNs are a little dumb because they're just like, you tell them, do this, and they do it. They're not at all. Hava Siegelman, a professor of mathematics and computer science at the University of Massachusetts in Amherst, showed in 1995, actually earlier in 1992 in her Rutgers dissertation, that they simulate Turing machines. So they are computers. Okay, so if you're a syntactician, they can do internal merge. And so most of what we need to do is to actually restrict them, but they're incredibly powerful computing devices. This may strike people as being odd because, Turing machines you learn about if you've learned about automata and, deep things that Chomsky talked about very early on in the 50s and 60s that most people have forgotten about, sadly, but that are the essence of the power of linguistic computation. And it may seem odd that we're raising them here in the context of deep learning, which is supposed to be kind of the opposite of linguistic theorizing, but they're actually not. They have very, very deep connections. So I'm just now going to tell you about my plans for using these kinds of devices. A lot of what's happening in AI today, which is what I'm hoping to use, is figuring out how to restrict recurrent neural networks within a self-supervised neural network framework. Sadly, the most recent kinds of devices called transformers are usually introduced by saying they're nothing like RNNs or LSTMs, but they're actually very much like them. But that's how just how people talk, and So I'm trying to use them to improve label performance and to replace multiple labels with a single label of the autoencoder. So notice what happens here is you have a whole, so imagine we have a whole set of labels during a certain segment. Now we can replace it with the code for just a single one. And I hope you see that that could be very useful for doing, so that it would say, let's say, this is a pause. From here to here is a pause. If you've ever done collected data and you're trying to label it, it would be nice to know where the pauses are, but I'm hoping it'll do a lot more than detect pauses. One could then learn phonotactic regularity using the kind of example that I showed you from English. And then it doesn't stop there. So if you're a linguist, but you're not a phonetician, you should know that John Goldsmith, over the last 27 years, has developed all kinds of computational devices for unsupervised morphology. And Alexander Clark has developed the possibility of grammar induction. Now, whether they can be helped by deep learning is a completely open question. But what I want to leave you with is this hope that deep learning and other associated aspects of machine learning can help us automate, a bit of what a linguist needs to do. It still does not replace a linguist, but and one of the most hopeful aspects of this is very recent work by Chris Manning and his students at Stanford has shown, so this is a paper from Proceedings of the National Academy of Sciences from June 2020, has shown that trees can be gleaned from numerical neural network representations of sentences. Even when the neural networks weren't told anything, they weren't trained on the notion of tree. So this notion that deep learning can really assist in documentation and linguistic processing in general, I think is greatly helped by this paper, because it shows you how trees are part of what is learned by a neural network. One last thing before I finish, I'm also working on using articulatory phonology together with improved acoustic and aeroacoustic models in case we need unlimited amounts of data, like that wave-to-vec paper that I showed you earlier, which suggests that we still need thousands and thousands of hours of data. So I'm using work that I've already done on the dynamics of transition, and then 2 new books that I would like to advertise. I don't get any money from them, so this is not some kind of shameful thing. So there are 2 books by Rich McGowan that have taken us way beyond what we've known about acoustic phonetics and the ability to generate spectra from vocal tract shape. And these are very recent books. This book is from about 3 years ago, I would say 2 to 3 years ago. This book is, I think, just came out last year. They haven't been cited as far as I've seen, but they're really beautifully written, understandable books, and they're very, very important. And I would like to advertise them here, and you can order them from there. Again, no money. I get no money from this. And this is going to be helped enormously if we know how the vocal tract actually changes and moves, so that we can generate dynamic data, synthetic, that actually represents how the human vocal tract moves. And here at USC, Krishna Nayak, Sri Narayanan, and Danny Bird, my colleagues, and I are building the first quiet MRI system that will allow us to finally get our area functions and spectra that we can actually study, because we can see the entire vocal tract as it's moving with collected audio that is not filtered. And this is, I think, going to really be wonderful for generating data synthesized data to train on. So let me conclude. So the primary work on endangered languages will always, in my opinion, be on what it has been, close linguistic analysis through contact with speakers. And I hope I didn't leave you with any other impression, but there is hope that this work could be assisted through deep learning compression of information. And there's no magic, sorry. Linguistic structure at all levels imbues language use with predictability, and deep learning is just a method to pull out what is unpredictable from a lot of predictable stuff. And if you've taken linguistics courses, you know that that's what linguistics is about anyway. And I hope that this will be of help. And that's it.
Okay, thank you. Thank you very much, Khalil. It was wonderful. It opened our eyes for so many aspects.
Great, thank you.
I don't work directly with deep learning or so many data like that. And now we are open for questions. As far as I could see, there is just one question, and I'm going to read it for you. But and I hope meanwhile other people can write down their own questions. So Joyce McDonough asks, how similar do the spectra need to be? The variation is huge. I think she's referring to the slides where you put us, you showed us the spectras.
No, I think it's really, so from the English example, there is lots of similarity because, however, there is speaker dissimilarity. So the fact that it's coming from, different types of people with different sizes of vocal tracts, etc., is introducing spectral variability due to speaker variability, which I wanted to kind of check in that first. So there is lots of similarity amongst the spectra that is in general saying, oh, the two first formants may be very far from each other or very close to each other, regardless of whether the speaker has a big vocal tract or a small vocal tract. What we see from the Ladin and the Guarani data is that you have silences, you have people pausing, you have all kinds of things that are happening over a small amount of time, and it's still doing pretty good reconstruction. So it means that the spectra don't have to be so similar to each other. And so I was very sort of encouraged by seeing that kind of data.
Okay. Okay, I hope Joyce is satisfied with this. I don't know if Eleonora says something. Eleonora is thanking you for the beautiful talk.
Thank her.
Thais Silva, thank you, Khalil, for your talk. I have worked with endangered languages, and this seems to be a promising way to research and document them. Amazing work.
Thank you. Hi, Thais. It's been a long time. I'm just saying hi to Thais and to Eleonora. It's been a long time since I've seen them. Yeah.
Okay, let me see if somebody else made a question earlier.
Maybe I can mention one more thing as you're looking for more questions. I'd be more than happy to, so I also don't want to have left you with the impression that this is some technicians are going to figure it out and then you can use this. I can explain to you everything technical in what I've talked about over a 20-hour period. So if people are really interested in learning how these things work, I'd be more than happy to do like an online summer school over a 20-hour period, over a couple of weeks or a month or something, where you can learn these things. So if you're really interested, contact me and I'll get together a group and we can do a summer school. I really enjoy teaching these things.
Great. Our committee is very interested in this. We have so many, so many activities in Berlin nowadays, and we can see it and do something together. So there are more questions now. Thais, how would work? Let me see if Eleonora. No, it's Thais first. How would work on perception follow from the work you presented? I mean, would the generate output be seen by the native speakers as good?
Yeah, that's a very good question. I haven't done any work on that, but that would be a wonderful thing to try well, I can tell you this from what I showed you today. Absolutely not. So I'm showing you kind of a glimmer of hope. I should have said a glimmer of hope for endangered languages, where there is some consistency that hopefully will become better. But whether the labels match perceptual labels, we really don't know, and that would be a very good thing to pursue. Yeah.
Okay, so Eleonora asks, can you collaborate on how the situational context is predictable? Say people have video records, for example.
So do you mean visual information?
Not exactly. The situation context, when the situation context is predictable.
So
instead of being only audio recordings.
Oh, I see. Yeah. So a lot of modern machine learning is about the combination of text and video. And there are, in your mailboxes, you may be getting things every day showing you how captioning is becoming a real thing, where you give a video and it gives you a small description in terms of text, or creating a visual animation from text, and things that seemed like 2 years ago would be impossible. Now, these require enormous amounts of data to really combine the two. So we're certainly not there yet, but there is nothing, if we're able to, for instance, synthesize video. So the late Eric Bateson and many others had worked on the synthesis of facial information from text. And if that kind of work we could do synthetically, just like I'm planning to do the acoustics, one could learn an enormous amount from that to enable visual and audio information. But we're not there for restricted data uses like this. For English, we can do a lot already, but not for endangered languages, as far as I know.
Okay, thanks. Continuing, Eleonora continues. Can we hope for that kind of help for field work?
I'm hoping so. So I've given up on predicting how long things will take, because maybe I can give, since we have time, I can give a little bit of my own. So for a long time, if I could just be a little autobiographical, I started work in phonetics really by looking at speech recognition in the mid-90s at the University of Illinois. And I concluded from that work that it is impossible to do anything interesting with machine learning unless we know everything about how the tongue moves and acoustics and all these things. So I ended up working. And then around 2005, 2006, a friend of mine showed me, the speech recognition, on my phone works. And I started to give him a lecture on it could never work because we still don't understand this and this. No, try it. I could make it fail, but it took a while to get it to fail. Now these devices are getting extremely, extremely good. I get messages in English and Arabic, and it's figuring out the English parts and leaving out the Arabic parts. I don't know. That's how good it wasn't doing that 6 months ago. So right now, when my brother, for instance, will leave me a message, half of it is in Arabic, and then you get some English. It's picking out the English part and doing a very good job on the English and leaving out the Arabic as gibberish. So these devices have gotten extremely good within my lifetime. So right now, I would think it would take a while before it becomes a useful field tool. But you know what? I don't know how long it's going to take.
Okay.
Yeah, the more people work on it, the more real it becomes. So I hope for people who are interested in learning, contact me.
Okay, so Thais is is saying, great Khalil, one step at a time, about the videos thing. And okay, and now we have a question from Fang Li. Thanks for such a great talk. Will there be a recording of these talks so that I can share it with my colleagues working with indigenous languages? Yes, Fang Li, we'll have this recorded and it will be on Abralin Ao Vivo page. Linguists Online is Abralin Ao Vivo, and then at the end I can write down for you, okay? Thank you for your question. And Joyce, Jonathan,
no, please. Yeah.
say
I was
something?
going to say it's going to be on YouTube, as far as I know, for posterity.
Yeah. Joyce McDonough. Sorry, Joyce, if I don't pronounce your family name well, but she asks, and responses, maybe it's a commentary, and responses of the auditor system.
Mm-hmm.
I don't know if you want to comment, Herc.
Yeah, I think that, yeah, so work that Joyce has been doing at the University of Rochester on the auditory representation of spectra or of the auditory signal, I've never thought about implementing, so instead of using spectra, to use auditory representations. That would be very, very interesting. I've never done that, but that could be very interesting. It could be that they're already compressed to a certain level, since they actually are, and could serve as much better first representations. Yeah, Joyce, let's work on that. Yeah, that would be wonderful to see if that would work better, even on just this very same data. Yeah.
So I will. I think we have some time, and I myself am going to make a question, and it's related to the beginning of your talk about that when we lose a language, we lose many things. Like you relate this to motor control, and it interests me a lot because I remember you on one of your talks in Brazil, talking so beautifully about how each language has a way of, each language has an apparatus, an articulatory apparatus that works like, I don't remember the metaphor, but maybe it was linked to tools, different tools to it. You relate this to, you have different tools to it, so you have different forms.
Oh, yeah.
And this is so beautiful, thinking that each language has its own format inside our oral cavity and larynx.
Sorry, keep going.
So just to finish, the question is how do you link this, how would you link all this data you can take, you can store, and you can analyze, how you can link this to a hope for us not to lose this beautiful movements. And I would say other things too, but I'm focusing on the movement, the articulation.
Let me actually answer this question with one of the first times that I really paid attention to it. So the work of Mary Beckman, for instance, one of the things that I got out of it very early on in my career is this notion that prosodic systems, which control the speech production system, can be so incredibly different from each other. Incredibly different. We tend to think like, oh, stress and things like that are going to be in so many languages, and that's not the case. All kinds of languages have very, very different prosodic systems, which have very different influences on how the vocal tract is moving, on the motor control of the vocal tract. So from very early on, and I think this is part of my training as a linguist, you see the beautiful thing that Chomsky and Prince and Smolensky and these great minds have put together, which is languages are arbitrarily different and arbitrarily similar. And if in a few decades have 50 languages instead of thousands and thousands of languages. The richness of what would the part of the human mind responsible for vocal tract articulation, for perception of speech signals, how these things work, let alone the rest of language, we will simply not be able to answer those questions. And that's just a loss to humanity. I don't like the word science being used in these terms. It's really humanity. It's just an unimaginable loss to humanity. Yeah. I'm not sure if I've answered your question, but you're certainly absolutely right. At the segmental level, it's even more obvious. So if we don't understand how the variations on the various what we're going to call them, gestures or features or whatever, that exist, if we just look at American English and Mandarin vowels and Dutch vowels, etc., it's just an enormous loss to our understanding of the human ability to use our biological structures.
Yeah, sure, totally agree. So let me see if there are other questions. Omer Preminger, it would be fascinating to see how an RNN trained on acoustic data versus one trained on ECOG data from auditory cortex would fare when we compare how much training data each of them requires.
Yeah, absolutely. So I'll give the same answer as I gave to Joyce. That would be wonderful to try. I haven't done it, but you guys are giving me ideas, so I hope we can talk about this. The higher you go up, so I think Joyce has been working on midbrain, but certainly cochlear or so we know from work in deep learning on language that using MEL spectra is already better than using linear spectra, which is what I've been using, or so BARCs or MELs. And we've known this in acoustic phonetics for a long time. So that's already kind of telling us that this is a good way to go. And you're absolutely right. And yeah, I'd love to talk more about this, but it would have to be done. I haven't done it, so I can't answer it from experience, but I would imagine that it could provide with more consistency across the labels.
Okay, thank you, Khalil. I think
thank you very much.
Question. Oh, this question was very much, okay, Omer is doing comment. Yes, this question was very much inspired by Joyce's. And there are some people saying thanks again.
Thank you.
Thank you. Thais says thank you, Khalil. I'll be in contact soon. And Joyce says excellent, very relevant to the work that we are doing. So, okay.
Great, thank you, everyone.
I'm going to thank you again, and I have to pronounce some final words. But after you, sorry. Do you want to say something else?
I just wanted to thank you again and to thank everyone who's attended, and hopefully people who will watch it later. And I hope it inspires people to work on endangered languages. That would be the biggest, sort of. And again, you're more than welcome to write me. I'm easy to find on the World Wide Web, and I'd be more than happy to talk with anyone more about this.
Okay, great, Khalil. Thank you again. So my final words are to encourage all of you and to spread our event, that's Abralinha ao Vivo, Linguists Online. And if you're not yet an associate, please be an associate of Abralinha. Abralinha is doing an amazing job since May 2020, and I'm very pleased, and it's a great joy to be here for the third time, and especially with you, Khalil. Thank you so much.
All right, bye everyone.
Okay,
thank you.
Bye.
Thank you, Dale.
Bye. So bye. For Please take a look at Abralinha ao vivo in your notes. Thank you.